All right, Luca, anytime you're ready to go, you can start going.
Amazing. Good evening, everybody, or at least it's evening here in London, 9 p.m. And on the last lot, it's been a long day. You've been through a lot of talks, and I hope we're going to make this worth it. So in the next 40 minutes, we'll be talking about TrueLayer, the company I work for, and most importantly, about our journey adopting Rust, a fairly new programming language that most of you, I'm sure, have heard about. Before we get into the nitty-gritty, I just want to get introduced to all of you who I've not had the pleasure to meet. My name is Luca Palmieri, and I work as a principal engineer at TrueLayer. You can find me on Twitter. The username is AlgoLuca. And in terms of what I do, apart from working at TrueLayer, you might have seen me if you've been engaged in the Rust community. So I contribute open source software of various kinds. And I'm mostly known for being the author of Zero to Production in Rust. Zero to Production in Rust is a book that introduces developers to the Rust programming language, and most importantly, on how to use Rust to actually build backend services. And that's going to have a lot of intersection with what we're going to be discussing tonight. The talk is roughly divided in 3 sections, in case you want to wander off and come back. The first one is going to give you the state of the union at TrueLayer, like the numbers. What's Rust at TrueLayer today? But then want to discuss more broadly, in a somewhat Rust agnostic fashion, what it means to adopt new technology. What are the challenges you face, and what type of considerations you should be making. And in the end, we'll go back to Rust and actually get into the nitty-gritty, like why did we choose to take a better Rust? What did we see there that we thought was worth the risk? So without further ado, let's get started. And yeah, I think there was an apt GIF, because this is really a story, and a story on a fairly long time scale, 2 years, more or less. Now, May 2020, this is 12 months ago. I know it seems it passed in a few seconds. At TrueLayer, there were roughly 30 developers working on application development. None of them was using Rust on a daily basis. Out of all the microservices we were running at the time, whose number I was not able to reconstruct yesterday, only one of those was written in Rust. It was a demo application for our payments product. We used it to allow people to donate to charities to support communities impacted by COVID. It was not a mission-critical service, so fairly on the side of our main products or our main services. And that was roughly 4,000 lines. We had no internal ecosystem at all. There were no private crates at TrueLayer that we used to share logic and functionality between applications. Now, if you step 12 months afterwards, the situation looks remarkably different. We have 14 developers at TrueLayer using Rust on a daily basis, out of the 60 that compose the whole engineering organization. That's what they use on a daily basis to build services, to troubleshoot, to do everything that concerns their job. That's roughly 1 developer out of 4. And we find the same ratio in our microservices, so the things we run in production to actually provide services to our customers. 28 out of 117 are written in Rust. We have 165,000 lines of Rust code, which is starts to be a sizable real estate. And 54 crates that we use to share cross-cutting concerns such as logging, metrics, and just generally avoid repeating ourselves across services. Now, that's quite a stark change, right? You would say that was a pretty fast adoption journey. And it's then what helps to put it on a timeline, like look at it quarter after quarter. The first Rust adventure in production was started in Q3 2020, so roughly 12 months ago. TrueLayer decided to write a new product suite called PayDirect. And the first part of that product suite was Payouts API. Payouts API, just to give you like the ABC about TrueLayer does access to banking services. So we provide connectivity to banking providers, and we allow people to pay using their bank accounts. And up until that moment, we were mostly acting as intermediaries. So the customers would come to us, and we would instruct the banks to do something. In Q3 2020, we were doing something new, something bold in many ways. We were launching a product where we were actually managing funds on behalf of customers. That was Payouts API, allowing merchants to pay into merchant accounts managed by us, which they can then withdraw and pay from. This project started with 2 engineers, myself and a colleague, James Smith. And this project started in Rust. We built for most of Q3. We hired as well. And in Q4, we had 6 engineers working full-time on this, and we actually managed to launch a project. The project was commercially successful, and we ended up hiring more engineers, and we built another API, PayDirect API. And we had even more engineers afterwards to build stuff that I'm not allowed at this point in time yet to discuss. And so you might say, well, that was reasonably fast, right? Like every single quarter, we added 4 engineers, and we launched new stuff. But it's also reasonable to say that it wouldn't have been as fast if we were not have been lucky having launched a product written in Rust, which turned out to be successful and led us to write more Rust, which is certainly the case. But the question you really need to ask yourself is, why did we, in Q3 2020, actually believe that Rust was a viable option? Why did the CTO and the rest of the engineering organization, why didn't they say, what the fuck are they doing? Like, why are we even considering Rust? TrueLayer at that point in time was using .NET, in particular C#, for almost everything that was backend. Like, what was the need to introduce a new language? Well, the truth is, these 12 months are not the journey, they're just the outcome. It's what you see at the end of a journey that started much earlier, actually 12 months earlier. So 2 years ago, Q3 2019. TrueLayer was a very different company. I think engineering had 10, 15 people at most. And we had one product called Data API, which is the one that we use to allow customers to access banking data. And we were starting to onboard some serious names in the UK fintech ecosystems. And some of those customers were stressing our capability to handle traffic because they were sending high volumes in short bursts. And we were experiencing very high tail latency. So the 95th, the 99th percentile on that API were not performing as well as we would have liked them to. So we had requests returning in 1 second, 10 seconds, 20 seconds. And the point was that those requests should have not taken that long. They were just coming into the API, and we were pushing some task on a queue to be processed asynchronously. That should have been fast. But the truth was we were having garbage collection issues. So we had GC poses, and we were having issues troubleshooting. And so in anger, I think over a weekend, me and a colleague actually brought a POC of that part of the API. I said, well, if the problem is the GC, let's do a version without the GC. And that POC actually worked. But we never ended up deploying it. It was not a good idea at the time. We didn't have the skill set to maintain it. We managed to solve the problem staying within the .NET ecosystem. And generally speaking, Rust was not mature enough in Q3 2019 to be used as a backend language. But we didn't give up. Like, we kept flirting with the language. I think that's the metaphor I like to use. And so we started writing small, non-critical components, small Kubernetes controllers. We brought a bunch of CLIs. So we had Releaser that we still use today across the whole of TrueLayer to manage CI and CD. We had Sherlock, which we wrote specifically for our operational stuff to troubleshoot specific kind of issues. And then we started to engage with the community. So we started to be the host of the Rust London user group, the biggest and oldest Rust meetup in Europe. And we also gave TrueLayer's employees the chance to actually upskill themselves. So those of us who had not been using Rust for hobby actually got some time and some training from Ferrous system on actually how to use the language and to understand what it feels like. And then COVID in Q2 stopped everything. But the point is, it was a long journey until we were ready to seriously consider Rust as an option. Which leads us very nicely into the second part of this conversation, which is, what kind of questions do you actually ask when you're about to adopt a new technology? Through this, and most developers know this, although they don't like it, and I put myself in that group, that introducing new technology increases risk. And that's because when you're looking at new technology from a point of view on, is this going to help us getting what we need to get done, you actually arrive at this matrix. And I'm sure many of you, especially those with a background in management, have seen this before. Known knowns, known unknowns, unknown unknowns, unknown knowns, which reads very weirdly and stresses my English pronunciation. But saying that in a language that we can both understand is, when you're starting a new project and you use a certain technology, there's a bunch of things that you know that are a risk, are facts or requirements. You know those at the beginning, and they're part of your project plan. So you either choose to address them, you choose to address them later, they're managed, like their requirements. That's something you know, and it's being managed. Then you have known unknowns, something that you know you're going to struggle with. You don't necessarily know the details, but you know it's there. For example, if you have an API, you know that suddenly, instead of serving 10 requests per second, you start serving 1,000 requests per second. Some stuff is going to break. You don't know the details. You don't know what exactly is going to explode, but something is going to explode. So that's an area of risk that you're aware of. Then there are unknown knowns, something that you are not aware of, but somebody else is. That somebody else might be a colleague, might be somebody in another team, might be somebody in Stack Overflow, or somebody as part of the community of the technology you're using. So you're going to be surprised, but you're going to be able to find help somewhat fast, and you're going to be able to fix the issue. And the last quadrant, and that's where stuff gets seriously wrong, it's unknown unknowns. Stuff you're not aware of and nobody else has seen before. So when you actually have one of these unforeseen risks, you are on your own and you need to figure it out. Now, imagine that you have this matrix for every single piece of technology that you choose to use within a project. So the more technology you have, the more likely you are eventually to bump into one of those unforeseen risks, which leads to a famous talk and a famous article that I'm sure, once again, many of you have seen from Dan McKinley called Choose Boring Technology, which basically boils down to one thing. The more time passes, the more some unknown unknowns, so some unforeseen risks, become some unknown knowns. And that's because there's a higher likelihood that somebody else will bump into issues, they will sort them out, and they will share the knowledge that they acquired, either by fixing bugs, if it was a bug, or documenting the issue, and so that you know when you're designing the system that might happen. So if you stick to technology which is being battle tested, so it's been around for 5, 6, 10 years, and has seen extensive production usage, the likelihood of you actually finding, I don't know, the Postgres bug is very, very low. And so the risk on your project is equally low. Now, of course, if you apply this in an extreme fashion, then we'll still be using technology developed in the 1950s. Not that that doesn't work, but we have figured out some stuff in the meantime. So you want to find a balance, right, between lowering the risk for the project overall and actually advancing the state of the art. And Dan McKinley understands that. And the concept that he gives inside his talk is called innovation tokens. So every time you're starting a new project, you have a bunch of innovation tokens to spend, some budget that you can use to actually try some new technology. He says you have 3 innovation tokens, and once they're out, they're out. So you can only make some new choices. The rest has to be boring technology. But the question, of course, immediately arises, is like, how much is an innovation token? Like, is it Bitcoin? Does it go up and down? Or does it have like a stable value? Well, the truth is that it helps to think about technology as a pyramid. You have libraries at the bottom. Many inexpensive developers are usually the ones in charge of choosing which libraries to use or not to use. Then you have frameworks. These are big. They're entangled with the stuff you do, but they're still language specific. Then you have programming languages, databases, and cloud providers. And the higher you go in the pyramid, the higher the cost of a mistake. You choose the wrong library, well, it's going to take a few days, maybe a sprint, and you're going to read it out and use another library, or rewrite it and write your own. Choose the wrong framework, that might take a while to fix, because it's calling your code, you might be entangled, but eventually you're going to get it out. You choose the wrong programming language, well, now you need to rewrite it. If it was a big service and the original orders are gone, that might be pricey. You choose the database and you didn't realize it was not for your use case, and you find some subtle concurrency bugs. That's going to be a hell of a lot painful to troubleshoot, first and foremost. And secondly, you're going to have to migrate your data. And that might require you to have some downtime, so not pretty. And well, cloud providers and container orchestrators, migrating from one cloud provider to the other is a multi-month or multi-year project. Most of the times, multi-cloud, we all know how that goes. So the rule of thumb is the higher you are in the chain, the more innovation tokens it costs. So if you're choosing a new framework, maybe you can choose a new framework and a new library. If you're choosing a new programming language, maybe you should stop there. And the same applies to databases. Now, but we chose to use a new programming language, right? That's the whole point of this talk. Like, I'm here because I'm here and say, oh, TrueLayer has done some cool things. We use Rust. Look at us, new and shiny. Well, we did some serious thinking without actually going down that path. Let's zoom a little bit on programming languages, right? What's the risk? So we already said, like, if you make the wrong choice and you end up regretting it, you will have to do some rewrites. Not pretty, takes time, you're wasting engineers' time. There's other risks specifics to programming languages. The first one is ecosystem split. Suddenly, you don't have one ecosystem inside the company. So if you need to write a library, for example, for logging, and you have one programming language, you write it once, everybody uses it. Now you have 4 programming languages, and you need to write 4 libraries. And each of those libraries will have bugs, and they will have to be maintained and troubleshoot independently. So the total workload of the stuff you need to maintain has increased. You're also going to experience friction in moving people from projects to projects. If everything was written in JavaScript, it would be fairly easy from one person to move from one JavaScript project to another JavaScript project. The only thing they need to learn when they switch is the domain. Maybe they were working on the auth server, and now they need to work on the, I don't know, user system. Now they need to learn the domain and the language, which makes it a double jump, and that can be troublesome. So you risk creating silos because people don't move as freely inside the company as they used to. Then you might have some cultural words, like people are very religious about programming languages. So if you try to introduce a new programming language, you might face some friction, like, are you saying the stuff we use is not good? Like, do you want to rewrite everything? Like, it's very easy to get into a hostile climate, and that's not what you want. Lastly, but absolutely not least important, that is hiding. Like, developers care about the programming languages they use, not just because of the quality of the tool, but because it impacts the opportunities they're going to have and how marketable they are as developers when they go and try to apply for a new job, which they will eventually. And so they might shy away from companies using very old tech stacks because those skills are not marketable, so they don't want to go there. But at the same time, you might struggle to find developers for the newer and shinier stuff because simply they're known out there. Because nobody wants to be the first one to actually find those unforeseen risks. So everybody waits from confirmation from other pioneers, which might or might not happen. So you might end up in a situation where you cannot hire and you need to train internally, but you don't have the skill sets. And so eventually that technology dies. So all of these are very real risks, right? But in the end, as I said, I spoiled it at the beginning, we chose to use Rust. And we've gone pretty big on it, like you've seen the numbers, there's 14 people doing it. So something somewhere must have convinced us. And this is exactly what we're going to talk about, like what did we like of Rust? Well, I'm going to start from the pros because I spent the last 5 minutes scaring you. And at this point in time, you probably are like going back and deleting old services that you've not written in your main programming language. So let's start from the stuff that was exciting, like the stuff that got us pumped actually about Rust. And I'm going to start from the thing that I love the most, and which honestly was a solid 55% of why we chose the language, was the possibility of composing functionality from smaller pieces into larger, more complex pieces. And some of you might like be a little puzzled now and say, well, isn't that what functions do, or what classes do? So I'm going to drive the point home with an example. Let's look at this function. This is Python. I've been a Pythonista for many years. I still love the language. Please don't burn my house. This is not on you. This is just to prove a point. Now, there's a verify signature function, right? The point about abstractions is that they lower the cognitive load of the person using it. I don't have to care about how the abstraction is implemented. I can just care about the interface and get my stuff done. Now, what does the interface here tell me? Well, it tells me there's an asynchronous keyword. So this means that this function might perform some kind of I/O. This I/O might be reading files. This I/O might be over the network. So they might be sending stuff to a remote server. And that's pretty much it. It doesn't tell me much more. I mean, yeah, there's a token input, but that could be whatever. There's a lot of questions this function signature is not answering. What's the expected input structure? Like, what is that token? Is that token mutated? Like, do I need to like reason about what is going to happen to the token after I passed it into the function? what is the function going to give me back? It's called verify signature, right? So it might return me a Boolean, like true if it's verified or false if it's not. Or maybe it might throw an exception, like Python is an exception-based language. And what exception is it going to throw, for example? What do I need to prepare myself to catch? None of these questions are answered by the signature, which means that this is actually not an abstraction, because myself, as a developer, I am forced to either read the documentation, assuming it exists, or most likely I need to go in and read how the function is implemented. And this is particularly awful when it comes to exceptions, because some of you that have done Python recently might say, well, you can add a bunch of types, right? You can add types in the input and the output, so you're going to get at least like what the input and the output is. Yes, that's still not going to tell me how stuff fails. To know about exceptions, I need to go inside the implementation. And it gets worse and worse, because if verify signature calls other functions, I need to know what those functions can throw, unless verify signature is wrapping everything that gets thrown. So it quickly limits how deep my abstraction tower can be, because actually it's not an abstraction, it's extremely leaky. I need to go in and understand every step of that pyramid. So in the end, I actually cannot make a tower that is very high. That limits how much I can encapsulate. Now, of course, as you might expect, let's look at the same function signature, but this time it's written in Rust. Well, there's a lot more here. So it's still asynchronous, so I know it performs I/O. I know what the input structure is. So it's a JWT type, it's a JSON Web Token. I can go and look at the type structure. And that probably also has some invariants that I can care about. I know one thing which is extremely Rust specific, and it's given to me from the ownership system and the borrow checker. I know that we're passing in an immutable reference to that JSON Web Token, which means this function is not mutating it. So that's one less thing to worry about if I'm troubleshooting. I also know this function can fail, and that's because Rust represents failures instead of using exceptions, using a type called result. Result tells me the type of what happens when the function succeeds, and tells me the type of what happens when the function fails. So I know exactly all the failure modes. I just need to go and look at verification error. I don't need to go and look at the implementation. There's nothing that I want to know which is not contained into the function signature. I can use the function signature and be done with it. This means I can build higher and more robust piles of abstractions. Exceptions always make your software fragile, and that is something we experienced at TrueLayer very, very directly in many incidents that we had. Exceptions create implicit dependencies between different parts of the code base. And those dependencies are in the minds of the developers when they write the first version of the software, but then those developers forget because time passes. They leave the project. They either leave the company or move to something else. New developers step into the code base with fresh eyes. They don't know those implicit dependencies, and then bug happens. And the same happens, for example, with null references, which once again in Rust are instead controlled by the type system. Being able to encapsulate stuff effectively is what provides a lot of the value that we get from Rust, which you might argue is a value you get in many functional programming languages, and that's absolutely the case. So this is not unique to Rust, but Rust's type system is a pragmatic approach on a lot of things that have been around for many, many years, in Haskell, in OCaml, in F#, and many other languages of that kind. The second one is once again a flavor of the type system, but I want to point this out specifically because it's so, so important to enterprise development, and that's the possibility of expressing state machines. A state machine is something very, very simple. You have an entity inside your system, and this entity can exist in different states. Let's take as an example a user. When you first roll out the first version of your platform, you think about users in two states. They're pending and they're active. Pending is when they compete, like where they fill in a sign-up form. They receive an email, but they haven't confirmed yet, so they're pending. The only thing we know about them is that they have an email. Then they click on the email, and now they're active. So now we know when they confirm the email, and now they can do more stuff on our platform. The extremely powerful thing about Rust is that enums can have fields, which looks so stupid, right? But it actually is a game changer. And that's because in other languages, you have only one way, but two ways of expressing polymorphism. So expressing ways of changing behavior. You have class hierarchies. So something is a subset of something else, and lots has been written and said about why class hierarchies can be problematic. And the other one is you have interfaces. So I have an interface and I have somebody that implements the interface. The problem with interfaces is that you can have an unbounded number of implementations. Enums instead allow you to have a finite and enumerable number of variants that belong to it. So you can use this thing to use exhaustiveness. What this means is that every time you use a user, you can change the behavior based on the variant of that user. And the compiler is not going to let you proceed until you actually check in which of those states you are, which is very, very powerful. The most important thing is that this is future-proofing. What does this mean? Now, you'll start a platform saying, oh, I want to get users. I want to do user acquisition. So you focus on pending and active. Eventually, somewhere, somebody does something that they shouldn't have done. They break the terms of service, they embarrass you, they try to destroy your platform, you name it. And you say, well, I want to be able to suspend users because, I mean, these people need to be stopped. So you introduce a new suspended state. And of course, users in suspended cannot do all the things the user that are active can do. Now you've got a problem. Like you already have a code base which is fairly large, which has maybe tens of thousands of lines. And now you need to go and in every single point where you're manipulating a user, you need to also account for the suspended state. Very recently, I was reading a book called Philosophy of Software Design. And there's a whole chapter on comments. And one thing that the author says is that this, the one I just screenshot, it actually is a photo, not a screenshot, is a great comment. There's a status enum, and there's a comment explaining to the developer that every time they add a new status, they need to go in these 7 places and make sure that they're handling the new status. The author thought it was great. When I read it, I was like, what the fuck? Because this is extremely error-prone. Somebody might forget to add a comment the next time they're using one of those status variants. Somebody might not read the comment. That's unfortunately very common. Like people don't always read the documentation. And what this means is that you might fail to update all the code insights. And this might have more or less atomic consequences depending on the code base and what type of problems you're solving. What we want is we want machines to do this for us. And there's a very good machine here called the Rust compiler. The Rust compiler knows that enums have a finite number of variants. And every time you use a match statements, you need to handle all of them. So suddenly, the moment you introduce a new enum variant, the compiler is going to say, you have 50 errors. You're using this enum here, 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 and there. And until you tell me in every single one of these what you want to do if the user is suspended, I'm not going to let you compile this binary. And this is great, because this means that somebody who is new to the code base, or has spent the last 40 years working on this, can go and do this task because it's easy. Because the compiler is helping them scaling their knowledge, which is what we want to use technology for, to scale what humans can do. Now, got excited. Predictable performance. Like everybody, when they say, oh, you're using Rust, what are you writing? Embedded software, stuff that needs to be 3 nanoseconds. Yeah, I mean, Rust is fast. But through this, in most cases, doesn't matter. And in TrueLayer's case, honestly, doesn't matter. Like there's few instances where we really couldn't get to the performance we wanted using Ruby or Python. I'm sure we could. What matters here, and that's the important adjective which I've added, is that performance are predictable. And I'm going to use this example from Discord. So Discord recently, well, last year, reported a service from Golang to Rust. Golang is represented in purple in those screenshots, and Rust is represented in blue. It doesn't matter that Rust is fast, and of course it is, because in their implementation allowed them to do certain things. So it was like 10x faster or something like that. What matters is that the Rust line is flat. So taking a certain action roughly always takes the same time. So the average response time of the system and the 95th percentile of the system are completely horizontal. There's no GC. There's nothing that from time to time that you don't see and says, oh, let me do some work. Not to say the GCs are useful, they're extremely useful. They're very sophisticated pieces of technology, but they make it more difficult for the operator, for the person who's troubleshooting the service, to actually understand what's going on. Instead, having a very predictable performance line makes it much easier to spot when things are not behaving as expected, and to do stuff like scaling and capacity planning. So life easier, but well, we like that. Fourth, and this I could not stress enough, when you choose a programming language, you're choosing a community. You're choosing a group of people you're hiring from. If you don't like that community, you're going to have a very, very hard time, because those are the people that are going to respond to your job posts. Those are the ones that are going to apply. Those are the ones you're going to meet at conferences. Those are the ones you're going to read blog articles about. And if they're not nice, if they're not inclusive, if they don't share the values you share, then probably you've chosen the wrong technology. It's not enough for the tech to be good. It's the socio-technical ecosystem around that technology that needs something you buy into. And we definitely bought into Rust. It embedded a lot of the values that we wanted to see inside TrueLayer. And that is something that has actually happened. And it's one of the most positive things that has come about us using Rust. Not just the speed, not just the reliability, but the type of people we'll be able to engage. And we would do this again and again and again if we could. Last but not least, let's be very real. When you're betting on a new technology, there's one question that's really, really scary if you're a CTO or a VP of engineering. Is this thing going to be around in 2 years or in 3 years or in 5 years? Like, new programming languages die. D was on a great trajectory, is not going places at this point in time. It's still there, of course, the community exists, but it's not growing. And that's maybe not the type of technology you want to bet on, especially on a grander scale. And so we definitely did some work. Like, okay, is this Rust thing going to be around? And I mean, it was easier in this case. Like, everybody, all the big names are betting on Rust for various use cases, for various reasons. Mozilla, AWS, Google, Linux, which, I mean, it's the most unthinkable out of that bunch. They're all betting on Rust for their own use cases. So the Rust programming language is safe. Has achieved what a lot of people in the community call escape velocity. Like, this is not going to die. Maybe it's not going to grow forever. Maybe it's not going to become the major programming language, but it's going to be here and it's here to stay, which was an important thing to check. Now, not everything is roses and rainbows, so let's talk about risks. So let's talk about the things that gave us pause. Like, okay, like, oh, is this going to be okay? Number one, learning curve. Rust is a difficult language to learn, or so the legend says. Through this, it still takes some time to learn Rust. It takes weeks, sometimes can take a month or two. But of course, being working on the assumption that there were not many Rust developers out there, we were like, okay, can we train people fast enough? And when you talk about risk, what's important is not necessarily just to assess how big the risk is, but it's to have a de-risking strategy. Like, how do we verify that this is not going to be a major problem for us? The way we did this was by injecting people with no knowledge whatsoever of Rust at every point in the project. When we started in Q2 2020, it was myself and James Smith. James Smith never touched Rust in his life. He is very good, extremely experienced C# developer. By having the two of us as the starters of the project instead of two people which were very experienced with Rust, that was actually a first test to see, can James, who's a great dev, actually pick up this technology? Are the resources there? Does it make sense? How's that going to go? And we did the same at all points, injecting mid-level developers, people coming from JavaScript, people coming from Python, and see how they reacted and how they learned. And now actually we're fairly good at teaching Rust. We know what people struggle with, we know the best resources based on the background, and hopefully we can shrink that learning curve as we go forward. The second risk was ecosystem readiness. So yes, Rust was hype technology, was there to stay, so it was not dying. But are the things we need there? Are the web frameworks there? Is there a library to talk to AWS? Is there a library to talk to RabbitMQ? So what we did is we checked that the major boulders, the foundational pieces were there, and they were. And they were in a state where they were more than usable and battle tested. What we accepted, though, is that some of the smaller pieces were not going to be there. So we might have to write our own JWT middleware, some specific libraries. And that was a price to pay. Like, when you're in a young ecosystem, you need to factor in that you might have to patch stuff upstream, you might have to write your own things, and it's going to take some time longer. So that's a risk we accepted. And third one was the talent pool. Yeah, that's great people in the Rust community, but the language reached 1.0 6 years ago. So unlikely to find people with 10 years experience. You need to be sure that you can actually channel enough talent to balance the learning curve. So you want to be able to train people, yes, but you also want to be able to hire experts. And actually what turned out to be the case for us, that we can hire faster for Rust than we can hire for other positions, because the technology is attractive, because there's actually more Rust developers than Rust jobs. So at this point in time, that mismatch makes it easier for us to hire. And generally speaking, we attractive people that seem to be actually interested in joining TrueLayer. So that has worked out for us, although it was definitely a risk. And last, and this is the one, unfortunately, there's not much you can do to mitigate, is bust factor. You're starting a new project, it's a new tech, we say there's a massive amount of risk. How many people inside the company do actually know that technology? And if they leave, what happens? And here you need to really take a hard look at your numbers and have a conversation and say, okay, are you here to actually take this technology to the point where it's self-sustaining? Now, that was some sombering ends, so the things that gave us pause when evaluating Rust. It's been a year, it's going well. I'm very, very curious to see where we're going to be in May 2022. Maybe there's going to be another open source node. I would be more than happy to give you a Rust, our journey update. But this is all for me. So if you have any questions, this is the moment to fire them off. I'm going to be monitoring the chat and the Q&A. Please shoot. In the meantime, I'll drink and recover.
Yeah, thanks, Luca. Yeah, not seeing anything come in yet. Maybe it's been a long day and everybody's all out of questions.
Oh, there's something in the Q&A. Okay, Randy's asking, what kind of tooling do you use? IDEs, etc., etc. We're using a mix of CLion and Visual Studio Code. Different people prepare different options. CLion has IntelliJ Rust, that works very well. Visual Studio Code leverages Rust Analyzer. So both have been fairly solid choices. What have you found to be some of the most difficult aspects of the language when ramping up devs new to Rust? It depends on the background, I would say. For people coming from object-oriented backgrounds, so Java, C#, Python, for example, they usually struggle with the more functional aspects of Rust. So enums, error as values instead of errors as exceptions, managing nulls by options. It takes a little bit of time for them to get adjusted. People coming from JavaScript instead, for example, especially if they've done React or similar front-end frameworks, they know all that stuff, that they're used to the functional paradigm, but maybe they might struggle with stuff like concurrency and multi-threading, because it's not something they're necessarily used to think about. So different backgrounds lead to different challenges. Warren is asking what testing frameworks are used for Rust. Rust ships with a unit testing framework embedded in the language, so you get it out of the box. It gives you the possibility of defining unit tests and integration tests, and frankly, we're not needed much more than that. What was the driving factor behind choosing Rust versus trying to fit C# into your needs? Well, I kind of spoke about that for the last 40. There are certain things that C# doesn't do. So null checking is definitely one of those. Exceptions, it's another one. Like you can't use the language in another way. Otherwise, you end up your own dialect in C#, which is equally terrible. The other one was also like the community and the spaces and the energy that we find inside Rust. So all those things combined actually led us to give this a chance. And I'm going to make this clear, like I touched upon this during the talk. The point is not to replace C# at TrueLayer. C# at TrueLayer is not going anywhere. We have a million lines of C#. I ran a quick computation yesterday. The point is giving people options. And then each team can choose the golden path that they prefer based on the problem they're trying to solve, their own expertise, and the constraints of the problem. So it's not A or B, is you have this on the table, pick the one you prefer.
Hey, Luca? Luca?
Yes?
Zach Dahl had a question just before Randy's there. You might have skipped over.
Okay. Which one did I skip?
Is there any particular aspect of Rust borrowing and ownership syntax that has been proven more difficult for people to grasp at first, or has it been pretty smooth to onboard unexpected devs into?
Okay, so we haven't onboarded any super junior developers on this project. We're always starting with people with at least 1 or 2 years of experience. And we haven't noticed a significant struggle, even if they were more junior than some of our seniors. Of course, there are more things that might not be used to. In this case, it's always up to refer them to learning resources, which didn't just explain Rust as a language, but also try to explain what problems those features were trying to solve. So the book, like for example, the one I wrote, was born exactly out of this need. Like I needed a resource which taught Rust and backend development combined. And so I didn't find one that I liked, and I never wrote one, pretty much. I'm missing a couple of questions, so let's go over those two. What's your favorite place to start with Rust for new developers? The Rust book. Like the Rust book is always the best point to start. Then if you prefer something a little bit more active and interactive, you can use Rust Links, which is a collection of exercises. I wrote myself a workshop, which is available on GitHub, called Build Your Own Jira with Rust, which is a test-driven workshop that you can do on your own and learn a few concepts. My book, if you want to do backend, is a great place to start. Rust in Action is another great book. Like if there's something that is not missing in the Rust community, it's beginner resources. Like really, you'll find plenty of extremely high quality material out there. Do I have any experience with GUIs in Rust? I have no experience with GUIs, full stop. Like not just in Rust, in anything. And what is your favorite Rust crate? That's a philosophical question. I really appreciate tracing. Like if I have to name one, I would name tracing. Tracing is an instrumentation framework to collect diagnostics. And it's been the best one I've used out of my experience in C#, Python. It's just hands down amazing. So that's one I totally recommend to at least check out, even if you're not using Rust and you're not using it. It's nice. And I think I got them all. So thanks a lot. I wasn't expecting so much energy at the end of the day. I think something struck a chord. It's been a pleasure being here with you, and maybe next time we'll do it in person. Thanks for coming.
Thank you so much, Luca.